So, and what's happened if, let me change color, red, green, okay, blue. What if lambda is smaller than 1? Instead, we have a contraction of my lambda A2 of my vector. Here. And sure. Sure. So it's lambda A. The two lambda are different, so call it lambda hat. So the multiplication by a scalar, by a positive scalar, is simply an expansion or a contraction of my vector. Nothing particularly exciting, I know, but it's graphical intuition. What if lambda is negative? If lambda is negative, what if lambda is negative? So here and here. Not only, say, here you have your A, so lambda smaller than 0. What are you doing? Here you have lambda. Oh, here you have A1. Here you have A2, and here we have our arrow. So if lambda is negative, assume that for a moment the absolute value of lambda is greater than 1. So if you were multiplying for the absolute value, you would be simply expanding your segment, or sorry, your vector. So where is lambda A1 and where is lambda A2? So here we have three, 6, 2, 3, 5. Here you have minus A1, and here you have minus A2. So 2, 3, 5, 2. So lambda A1 will be here, and lambda A2 will be here because lambda is negative. So my no lambda A will be here. So you take the verse of the vector, you expand the vector, in this case, because the absolute value of lambda, which is also called the module of the vector, is greater than 1. So change of verse and expansion. So well, sorry, no, forget what I told about the module of the vector. But there is another operation that will be extremely important in what follows, the inner product or scalar product of two vectors. The product of multiplication by a scalar defines a vector. The inner or scalar product instead is an operation between two vectors. So what is, how it is defined? So we take two vectors, A and B, each one with its coordinate, A equal A1, A2, AN, B equal B1, B2, Bn, and then we multiply the first coordinate of the first by the second coordinate of the second. The second coordinate, and we sum it to the second coordinate of the first time the second coordinate of the second plus the third coordinate of the third times the exact third coordinate of the second until exhausting all coordinates. And scalar product describe our idea of perpendicular or orthogonal in geometry. Two vectors are orthogonal by definition when their scalar product is 0.